All right, let's look at aromatic compounds. One of the oldest important aromatic compounds is aspirin. It's a very old pain-relieving drug that's still on the market today, and it's just acetyl salicylic acid. Salicylic acid is a molecule you can get from the bark of the willow tree, and it was described all the way back in the time of Hippocrates as being a treatment for fevers, headaches, pain, and so on. So aspirin's a very old compound, and salicylic acid is even older still. And salicylic acid and aspirin that's derived from it are examples of aromatic compounds. Now, the general population understands the word aromatic to mean compounds that have a smell, and certainly the history of aromatic compounds goes back to compounds that had an aroma to them. But now, to an organic chemist, aromatic compounds, aromaticity, are very well-defined concepts that have a very specific chemical meaning. So benzene is the simplest example, or sort of prototypical example, of an aromatic hydrocarbon. And it just has a 6-membered ring structure with one hydrogen in each of the carbon atoms, and has a planar structure. Naphthalene is where we add an extra ring onto this molecule, so we have 10 carbons, also still a planar structure, and we have 8 hydrogen atoms around those 10 carbon atoms. So despite their similarities of the structure of aromatic hydrocarbons and alkenes, obviously we draw them with double bonds, they're really quite different in structure, and that's because of resonance. So the carbon atoms within benzene are all sp2 hybridized, and we have 120-degree bond angles. And we can draw 2 different resonance forms for a benzene, for the structure of benzene. We can draw this structure here, but we can also use our curly arrows to move each one of these pi bonds around to the adjacent position. And we end up with the resonance form on the right. Now, when we can draw more than one resonance form for a molecule, that means that it's stabilized. That's a general sort of feature of resonance. So each one of these double bonds in these 2 resonance forms signifies the overlap of p orbitals in a edge-on overlap. So those p orbitals are oriented orthogonal to the plane, and they're on every carbon around that ring. So for a molecule to be aromatic, there's a certain set of rules that need to be obeyed, and these were developed by Hückel, this guy over here. So the molecule must be flat or planar. It must have at least 1 p orbital on each atom of the atoms within the ring. And then we must count up the number of pi electrons that are formed amongst those overlapping p orbitals. So, and they must fit the rule 4n plus 2. So if the number of pi electrons matches that where n is an integer, then the system is considered aromatic. And so if n equals 1, then 4n plus 2 equals 6 pi electrons. And that's the situation we have with benzene. We have 6 pi electrons, 1 from each of those p orbitals that's overlapping, as we can see in this diagram over here. So in that diagram, each p orbital is overlapping, and there's 6 of them in total, so 6 pi electrons, so meets Hückel's rule, and so that benzene is an aromatic compound. Now, aromatic compounds are very common in organic chemistry. We use them for all sorts of reasons. We can use them as solvents. We can use them as starting materials for reactions, as reagents, and so on. And the chemistry of aromatic compounds goes, right back to the birth of organic chemistry, really. So the nomenclature of aromatic compounds is really quite simple. We just name the compound. If it's a benzene-containing compound, we name it as a substitute of benzene. And so in the case of this compound over here, we've got a methyl group, so it's just methylbenzene. Here we've got a nitro group, so it's nitrobenzene. Here we've got amino group, so it's aminobenzene. However, many aromatic compounds, particularly substituted benzenes, have been known for many, many decades and often over a century. And so they have common names that are really stuck. And so methylbenzene is toluene, and you'll never hear that molecule being called methylbenzene by an organic chemist. It's always going to be known as the common name toluene. Cumene is isopropyl benzene. Aniline is aminobenzene. Hydroxybenzene is phenol. Methoxybenzene is anisole. The aldehyde substituted benzene is benzaldehyde, which is from almonds. And the simple carboxylic acid is benzoic acid. Now, we can have benzene-related molecules that have more than one substituent, and when we get to that situation, the two substituents can be in different arrangements relative to each other. So if the two substituents are on adjacent carbon atoms, we call that an ortho-substituted compound. If they're on the 1 and the 3 positions, we call that a meta-substituted compound. And if they're on the 1 and the 4 positions, we call that a para-substituted compound. So the IUPAC rules, this would be a 1,2 compound, this would be a 1,3 compound, and this would be a 1,4. But traditionally, we've called these ortho, meta, and para, as shown there. Now, when we get up to more than 2 substituents, we can't use the simple ortho, meta, para, and so we go back to our numbering. And we just start with the part of the molecule that gives the molecule its name. So this is benzaldehyde. And we would start numbering so that we start with 1 being where the aldehyde is and number towards the first substituent, 2, 3, 4, 5, and 6. And so we end up with 5 bromo, 2 nitro benzaldehyde. Same with this one here. We've got the molecule as phenol as the stem, and then we number to the higher priority substituent, which is the chloro group. So 2, 3, 4, 5, 6. And so it's 2-chloro 6-methyl phenol. Okay, so unlike alkenes and alkynes, the pi electrons within an aromatic compound are not localized between any particular pair of carbon atoms. They're delocalized over the whole ring structure, and that delocalization gives the molecule extra stability. And that extra stability means they don't do the same sorts of reactions as alkenes and alkynes. So instead of undergoing addition reactions, like electrophilic addition, like alkenes and alkynes, they undergo substitution reactions. And these substitution reactions result in the replacement of a hydrogen with a new group while retaining the aromaticity of the aromatic ring. So these reactions are called electrophilic aromatic substitution reactions. There's a large variety of them, and they're incredibly important in organic chemistry. They often require a catalyst. Because the aromatic ring is stable, it takes a bit of an energy barrier to get it to react with an electrophile, and so often a catalyst is needed, and often these are strong Lewis acids such as aluminium trichloride. Here's a table showing the examples of the most common electrophilic aromatic substitutions. So we have halogenation. We can take a halogen such as chlorine or bromine and a catalyst such as an iron salt, in this case iron trichloride, and we replace a hydrogen with a chlorine atom. So we get a chloro-benzene ring, and the side product is hydrogen chloride. We can do nitration reactions where we replace a hydrogen with a nitro group, and we do those with nitric acid in the presence of sulfuric acid. And the byproduct is water in this case. We do Friedel-Crafts alkylation reactions. So this is where we take a alkyl halide or a haloalkane and a strong Lewis acid, aluminium trichloride, and we replace the hydrogen with a alkyl group. And so this goes through an intermediate, which is an alkyl carbocation. And then finally we have Friedel-Crafts acylation reactions, which is where we replace a hydrogen with what we call an acyl group. So that group there in the red box is an acyl group. And we get to that through using an acyl chloride or acyl halide in more general terms and aluminium trichloride as a catalyst. And we produce hydrohalic acid as the byproduct. So one of these examples we just talked about was the Friedel-Crafts alkylation reaction. That was an incredibly important reaction developed by Friedel-Crafts, and it was developed way back in 1877. So it's a very old reaction, but very important way of putting alkyl groups onto benzene rings. Okay, so that's a little overview of aromatic compounds. Aromaticity. Remember the 4n+2 rule developed by Hückel, and some of the reactions of aromatic compounds, which are most importantly the electrophilic aromatic substitution reactions. Thanks for watching.